Okay, let's get started. So, hello everybody. Welcome to the first review session for ENGR 210 for this semester. Today is 1/28/26, and today I'm gonna try to go over all of the topics that you've learned in the class so far that are like relevant to the projects and such. Um, So I'm going to be going over, and if I'm missing anything that you'd like me to go over, feel free to speak up. If you have any questions, if I'm going too fast, and if I make any calculation errors, be sure to tell me. But yeah, I have a couple topics. I'll just write them down. I'm just going to go over like Ohm's law, basic circuits, then sources, like voltage and current sources, then resistors and like parallel and series, then KVL, KCL. And have you guys learned source transforms yet? Do you know what that means? If you don't know what it means, then you haven't learned it. Okay, I will take that as a no. So I will not cover that. And then I'll just do practice problems with whatever time I have remaining. So yeah, I'll also touch on like power. Okay. So to start, very basics of circuits, we're going to start with a resistor, and this resistor has some current flowing through it, I. The resistor has a resistance R, and this will make some voltage across it, V. We represent these very straightforward equation, V equals IR. The way to think about this is you can either think about it as when I push a current of I amps through a resistor, it will create a voltage difference between the left side and the right side in the direction of current. Not the other way to think about it is that if I have some voltage across the resistor, then V over R amps will flow through it. So those are two different ways you can think about it. Yeah. The power for any component is going to be the current times the voltage. And the sign of this is whether power is used or is if it's consumed or created. So positive power is used, like in a resistor, dissipated as heat, is consumed, negative is generated. And we can calculate this based on what is called the passive sign convention. I will go over this real quick. This is something I don't think it was explicitly touched on in class, but it is good to know. I'm actually not sure. I should read through the slides a bit closer. But basically, it's saying for some arbitrary component, it's just some component, we don't know what it does, we don't care what it does. If it has some current flowing through it in some direction, and it has a voltage, so there's two cases we can have here, right? We can either have the current flowing, going to say the current's flowing in both directions. In both cases, it's flowing in the same direction, but you can either have a voltage one way or the other way. So basically, we're going to say if there is a voltage drop in the direction of current, this is a positive voltage. And if there's a voltage rise in the direction of current, it's a negative voltage. This will come up again in a little bit when I talk about KVL and going around loops. But it also applies for power. So when you're calculating power, this thing, since current, you can always think of current as positive in this case. Here it would be power equals I times V, and that's going to be positive. Here it would be P equals I times negative V, and that would be negative. You can also think about this like, you know that batteries generate power, and if I have a voltage source or like a battery, and it's in my circuit, it has a resistor attached, you can imagine, okay, current's going to flow out of this side. It's going to flow out of the positive side because that's how it works. And here, you know that batteries generate power and it's going from minus to positive. That is the case we had here. Therefore, this is going to be generating power. For some reason, it makes sense. when you like get further in the class, but we call that a negative power, even though it's generating power, it's chill. That's how it works. Okay. That'll come up more. I'm just gonna like, most of this is going to be me doing practice problems where I'm just gonna over explain everything I do. That's what I've heard is the most useful thing. So yeah. Okay, next up, I'll briefly touch on voltage and current sources. So voltage sources, they're the ones that's a circle with a minus and a plus, and it has some number. Let's just say it's like 7 volts. What this is saying is from between the two sides of the voltage source, there's a difference of 7 volts. So if I have maybe 0 volts here, then here I'd have 7 volts. But also, if I had 2 volts here, that would mean I have 9 volts here, right? So a key thing is that in life, there is no such thing as like absolute voltage. So if I had a circuit, as odd as it looks, that looked something like this, with some voltage sources that are not all like connected in the same way. Actually, I'll flip this one around just for the sake of giving an example. So there's no such thing as like an absolute voltage. Voltages are all relative. However, for the sake of simplicity, and because you kind of need to have some kind of reference for what 0 is, in basically every circuit in this class, you're going to pick a point on the circuit to define as 0 volts. If the class is taught as normal, and like I think just like generally most practice problems, it'll end up being like the line on the bottom of the circuit is 0 volts because that's what makes sense in our brains. However, it doesn't always have to be that case. I could just as easily say that this is 0 volts, and the circuit would also work. You'd just be thinking about it in a different way. What that means then is if I have this symbol means ground or 0 volts. This is, you have a triangle or this thing. These are not quite the same, but they both mean 0 volts. You can use whatever you want. That means, though, if I then had a 2-volt source here and a 3-volt source here, even without doing anything else in this circuit, we can say, okay, we've defined this point as 0 volts. And now this point, if we say, okay, here I have 0 volts, and there's a difference of 2 volts between the sides. Then here I would have negative 2 volts. And up here I would have 3 volts. Cool? Cool. The other thing is with dependent sources, it's the exact same thing. It's just maybe you'll have an equation here, like 3 times V2, and then V2 is like labeled somewhere in the circuit. That's all that is. Current sources, on the other hand, are telling you what the current is in a part of the circuit, basically. That's how I like to think of it. You will find in the lab that you will never like have a current source. It's not really a thing you can just like create. If you do more electrical engineering courses, you'll eventually learn like how to kind of make a current source, but it's not the greatest. But for the purpose of this class, you can kind of just think of current sources as components that are telling you what the current is in part of a circuit. So, for example, if I had like this circuit, and this said 2 amps, and this was like 4 amps, what this is saying is that, okay, on the wire that this is connected to for like this whole branch, you can think of it, the current doesn't change on one path. So if I have 4 amps here, then I have 4 amps here, 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 and I have 4 amps here. Same with this 2 amp source. All of that is going to be 2 amps, and nothing else about the circuit can change that. In the middle here, you will have a different current because there is this kind of junction. The current can change, but I will touch on that in a moment. Okay, and then likewise, you have dependent current sources where it's the same thing as just an equation. Okay, then briefly I'll touch on how to like combine resistors with each other, because that's something that can be useful. If I have 2 resistors in series and they are R1 and R2, then you can say that this is equivalent to 1 resistor with a value of R1 plus R2. It makes sense. Cool. One thing I will also say is so these are called in series, right? A lot of this should be review. I think you all took physics too, so that should be good. One thing I will touch on is that components in series, you can change the order of them and it does not matter. So in this case, you could, if you had a circuit where you had something like what you see on the left there, you can rearrange this as I've shown here. So if this was like R1 and R2, and this was R1 and R2, and then this, you get what I'm saying, I hope. So that's how you do things that are in series. Next up, we're going to touch on things in parallel. I've found that a lot of students will often think things are in parallel when they're not in parallel, or they will not think things are in parallel when they are in parallel. So really focus on what I'm saying here and make sure you don't mess this up because it'll bite you in the long run. If I have some kind of circuit where I all of a sudden have a split and there are two resistors that are next to each other, then I can approximate this as one resistor by the formula. There's a couple formulas for it. The most general formula is going to be 1 over 1 plus R2 plus 1 over 1 over R1 plus 1 over R2 is like your equivalent resistance, right? And this continues to work for like R3 and so on. However, specifically for the case of two resistors, so for two Rs, you can do some math and simplify this to R1, R2 over R1 plus R2. If you think about it, if you just multiply by R1 and R2, it'll do that. So that's parallel. And then there's a couple things that I'm also going to touch on about parallel. So just like how I said with things in series, the order doesn't matter. You can rearrange it as you want. It's the same with parallel things. So if I have a circuit that looked like this, and I had R1 and R2, then this is the same as a circuit that looks like this. And also, this reminded me of something that I will talk about right now, where this is going to be that R1, R2 over R1 plus R2. But actually, why did GoodNotes add AI? That's so entirely unnecessary that they would do that. But like you can rearrange stuff as you see fit with things in parallel. One thing that I will see students do in this class, and don't be this student. Sometimes you might end up having a circuit where, so okay, wait, really quick. When you have something like this, right, you can then combine these two into one resistor, right? Very cool. However, I will see students do something where, let's say the circuit was like this. All of a sudden, there's a third resistor here. Now, you cannot, these are not in parallel anymore, right? The way that you know things are in parallel, I'm going to write this in words because I really don't want people to mess this up. Things are in parallel if and only if, math notation, both sides are directly very connected by a wire. Got to be very direct. Okay, so in this case, for this example circuit I've made, these two components are in parallel. These two components are in parallel. But because there is a resistor here blocking this connection, right, these are not in parallel. Likewise, you might end up seeing something where, I don't know, maybe you have a circuit that looks like this, right? And you have, I don't know, some stuff, and you have some stuff, I don't know. Here, it might look a bit funky, but you can find that these two are in fact in parallel. Go back here, you think, okay, here, these two sides are connected by a wire, and these two sides are connected by a wire, therefore they're in parallel, and you can combine them as you see fit. Also, this is a bad circuit. This voltage source isn't doing anything. Pretend I didn't put that there. Okay. So, okay, that's that. And then one other thing with series and parallel, you'll never have voltage sources in parallel. It just doesn't really make sense. I'm not going to explain that right now, but it just doesn't happen. But for like current sources in parallel, they add, and for voltage sources in series, they add. So like this would be equivalent, let's say this is like V1, V2, V3. This would be equivalent to one voltage source. Pay attention to the signs that I'm writing of V1 plus V2 minus V3. I know I'm going over just like a bunch of random stuff right now, but I want to have it all be said because I feel like all of this is kind of important to know at some point. So let's say this was I1, I2, and I3. Then this would become I1 plus I2 minus I3. So that's just how you combine those things. Okay, now I'll touch on KVL and KCL. KVL is saying for any circuit, for any loop. So let's make up a circuit. It got some resistors. It got another voltage source over here. Let's even put another thing here with the resistor. Wow. And also let's put a resistor here so that it looks better under resistor here. Sure. So for any circuit, for any loop, a loop just being like a path that goes back to the same place. So this is a loop. This is a loop. This is a loop, right? So it's saying for any loop, the sum of the voltages in that loop is equal to 0. What you can consider this to mean is, so let's say, for example, we're starting at this point. I'm going to go from this side of the resistor to this side of the resistor. The voltage is going to change something, right? And then, so I'm at some voltage here. And then from this side of the voltage source to this side of the voltage source, the voltage is going to change. And then from here to here, it's going to change. And then from here to here, it's going to change. And then from here to here, it's going to change. What it's saying is that you should end up back at the voltage that you started at, right? So it's saying if I go up 2 volts here, or no, if I go down 2 volts here, and then I go up 2 volts here, and then I go up some volts here, and then I go up some volts here, and then I go down some volts here, I should end up back where I started, which makes sense because the voltage, you only have one voltage on a given wire at a given time, right? So like this kind of has to be the case. So the way that you do this, and the way that you hopefully have done it because you've started working on your projects by now, is let's say, for example, I'm going to label this like I1, label this I2, and label this I3, and this can be V1 and V2. And I'm actually going to flip around one of these so I can call back to a point that I made earlier. Now, if I wanted to write an equation for this loop, the outer loop, I could say, I'm going to, let's just start at this point. It doesn't matter where you start, but we can write a bunch of voltage terms for each component going around that loop. So for this first term, if we recall back to what I was saying about the passive sign convention, if you have a voltage rise in the direction of current, then that's actually going to be a negative voltage. It's confusing, but it'll make sense because you often have many more resistors than you have voltage sources, and so it's nice if your resistor things are positive. That's kind of it. And then here you'd have plus, okay, remember for a resistor, V equals IR. So here you'd have I1 times R1, because that's going to be the voltage across this resistor, right? V I1 R1. And then for the next voltage source, okay, we look at this and we say, okay, now we actually have a voltage drop in the direction of current. So this one would actually be dissipating power, which might be a bit confusing, but or it's not necessarily like the numbers, I haven't actually put numbers on here, but that's how it would be represented in the equation, right? And then for that resistor, you'd have I2, that was supposed to be a 2. And then for the last thing, you'd have I3R3 equals 0. And then that's an equation you can use to solve the circuit. Okay, now the counterpart is going to be KCL. I will copy this so I can use it again, because drawing takes time. And I still have quite a bit of time, actually. So we're fine. But anyway, let's erase some of this. What KCL is saying is similar to with KVL, how you cannot create voltage out of nothing. It's saying that if I start at some point in the circuit and then go around, I should go back to the same voltage I started at. KCL is also stating like a pretty straightforward fact. It is said as the sum of currents at a node is 0. I don't know what the yeah, sum of currents is equal to 0. What that is saying is, so like for example, let's look at this node, right? Let's say we label this I1, we label this I2, and we label this I3. At any point in this class, you can just label things, and as long as you keep your equations correct, you can name stuff whatever you want. But for this case, I'm just making an example. What KCL is saying here is basically that the current going into a node is equal to the current going out. It's saying you can't create current out of nothing. Just for the sake of convention, we say currents going in are negative and currents out are positive. Some people don't like that, but that's what you're going to do because that's what your graders expect you to do, and they will get very confused if you don't do that. So please do the convention as said. I just said, yeah. So for this case, if we want to write an equation describing this system right here, right, we can write it as such. And then if you wanted to rearrange it to make it make a bit more sense, you can also write this as just like I1 equals I2 plus I3, right? And that makes sense because if I have some amount of current going in here, then, and I have this 2 paths for the current to leave, then these 2 added together should get you the current that went in. And this is just the mathematical way of writing that. Yeah. And that's kind of it, I think, for the topics. Generally, just like as an overview for this class, this is at least the first half of the class. I actually don't know how this professor is going to teach it, not going to lie. But for the first part of this class, it's going to be like an algebra class where you just have to look at the circuit, create equations, and then solve the equations. And that's kind of it. It's pretty chill. You just have to make sure you are writing the correct equations. And yeah, I think that's everything I wanted to cover in terms of topics. Now I will just do practice problems for 35 minutes. If there are any particular topics you want me to cover, let
I
me
got
know.
a quick question, actually.
Yeah.
Are you gonna go over the way to solve it, like using matrices? Because I think that could be really helpful. I know a lot of us were confused when he was
Yeah,
showing. Okay, thank you.
I can do that. That's that's just like a general way to solve a system of equations, but I'll go over it, yeah. Mhm. You can
Do we need
just
to use? Sorry,
you
go ahead.
yeah. The answer is you don't need to, but if you know how to do it, it's just easier to do it that way. Um, I'll try to explain it pretty well here in a minute. Yeah, but you don't need to. In the past, like this is the first semester I've seen where the professor recommends doing that. So it's like fine if you don't. Trying to find a decent practice problem to do here. Hmm.
You're just wondering, is the matrix method easier than the one taught in previous semesters?
It's like kind of the matrix method isn't like it's not a circuit specific thing. It's just a general like math thing. If you have a system of equations, then you can solve it in like 2 seconds on your calculator using a matrix. So I'll explain that. If you've taken linear algebra, it makes sense, but a lot of the time, like people just introduce it as something you can do without explaining the linear algebra part of it. but I'll try my best.
Yeah. Also, like for that matrices thing, I'm in linear algebra, but I just started it. But
Mhm.
like a lot of times, you kind of have unknowns in your matrix, I believe, unless I was doing something wrong. But how would you even like deal with it if you have like an unknown in your matrix? How would you plug it in your calculator? You know, does that
Mhm.
make sense?
Yeah, so you should end up not having unknowns in your matrix if you're doing it right. Yeah, I think I found a problem that'll be good for this. Yeah.
All right, and then one more real quick question about KVL in general.
Yeah.
Um, you can only use those loops if it's just like a resistor and a voltage source, but if there's like a capacitor, you can't do it. Or how like when can you use the
Um,
loop? Isn't it like very specific to like when you can do it?
kind of. So you're probably not gonna. I'm not familiar with the the order in which he's going to teach the course this semester, but in the past, you basically just work with for the first like 5 or so weeks, which I guess we're getting towards the middle of. You're only going to be working with like resistors and voltage sources. So for now, you can use it whenever you want. When you get to working with capacitors, there's like other equations for that, yeah. However, the different thing with capacitors is like you have instead of V equals IR for capacitors, you're going to have a different relation. It's a V equal or no, it's is I equals C dV dt, right? So you have like different things, and this is also translated to like V equals 1 over C integral of I with respect to time. However, KCL and KVL still apply, right? Even if I have a capacitor here, like what I was saying with like if I go around the loop, I should end up back at the same voltage I started with. That logic is still sound. Does that make sense?
Yeah, that makes sense.
So these will always hold. It's just like the specific way you're writing these terms will change depending on the circuit.
Okay, I think he also did say like also you can't like he was kind of briefly going over the homework. Like the first problem, let's just say for example, it was
Mhm.
like a current source there. He was like, okay, use loops at these two. Like actually, it might have been three loops, and then this other loop is like don't use it there because there's a current source. So that's why I was kind of like,
Oh,
okay,
yeah. What he was talking about there is so let's go back to this example. Pretend this all of a sudden was a current source. Now, if I wanted to make an equation for this outer loop, what you have to think about is like, let's just say this is 2 amps. I don't know. All of the terms in this equation have to be voltages, right? Because this is a sum of voltages in like general, in physics, in engineering. If you want to add things together, they have to have the same units. So basically what that means though is you have to know what the voltage is across this current source. And there's not really any easy way to find that. Because like with a resistor, you know V equals IR. With a voltage source, the voltage is given to you. But with a current source, it doesn't tell you anything about the voltage. You kind of have to figure that out by solving the entire rest of the circuit first and then going back to it. So that's why they're saying not to do that. What you would do instead here is, okay, this would give you information to do like an equation relating to the current, where you have 2 amps there and you have some current there and you have some current there. You don't know what they are, but it'll, you know. And then likewise with actually, yeah, that's the main thing I want to talk about with that. It's just generally it's hard to do a loop equation when you have a current source in the loop because you don't know what the voltage is across that current source. Does that help?
yeah. And so like, is that the only time you should maybe do like a KCL first, or like how do you know if you should do a KCL first and then do a KVL or the other way around?
Um, Kind of just depends on what kind of sources you have, what you think would be easier. Hopefully it'll become clear in a minute. Or it'll definitely become clear as you work through more questions in the class. But
Okay.
yeah. Also for more resources, me and Melissa both have office hours. She's one of the other TAs. I think Dr. Johnson has office hours. And then I'm going to upload this video to YouTube. And on my channel, you can see 3 past semesters of review sessions where I go over other practice problems. They might be similar practice problems because I take them from the same source. But if you want to hear the same explanation again, then you can watch them there. Uh, okay. And then this question is saying find I1, I2, and I3. Using KVL and KCL. So generally, when you have unknown things, right? If I have 3 variables I need to find, then that means I need to write at least 3 equations that relate them to each other, right? Generally in this class, at least for especially in this first part of the class, what you're doing is you are writing equations using KVL and KCL that you write them until you have enough equations where you have the same number of equations as you have variables, and then you solve the equations, and then you're good, right? So here I can write a couple equations. So let's see. Let's start with a KCL equation. We're dealing with currents, so it would be really nice if we can relate all the currents to each other. So let's do one here. One thing that I will point out is even though, as I showed in this last part, like usually you think of doing these KCLs at a point, it actually is saying, okay, for this like entire wire, let's think of this as one block. You have your currents going in and out like that, right? So for this question, if I'm looking at this node, you really want to think of it as like this whole thing, right? And then now we have our currents like this, right? So here we actually have 4 terms in a KCL equation. So remember our convention that that currents going in are negative and currents going out are positive. So at this node, we'd have, let's say negative 2 amps. Don't need to be writing in red. Negative 2 amps, and then plus I1. They're capitalized. I'll capitalize them. Plus I1 plus I2 plus I3 equals 0. So that's one equation, right? Next up, what else can we do? We want to get equations that, again, are relating these to each other. So let's see. If we want to relate things to each other, and then actually one other thing I'll say, you want to like get equations that relate your variables to each other in unique ways. So the linear algebra term for this is they have to your equations all have to be linearly independent. So like one equation can't be the sum of 2 other equations, stuff like that. But generally it's just you want to write equations where it feels like each equation is actually giving you new information. So in this case, we know that like, okay, we've done a current loop, or we've done a KCL, probably a KVL would be good to do next. So let's pick a loop that deals with 2 of the currents. So for example, how about if we go like this, right? We know the voltage here, we know the voltage here, and we can get the current there, right? This is actually like a pretty good loop, because this if you were just like solving this as you go instead of like doing a matrix method, you can just directly figure out I2 here. But I'll like go through the loop. So if we're doing this loop, right, we're going to have, remember, think about if the voltage drops or rises in the direction of current. If it rises, then you have a negative voltage. It's backwards, but get used to it. So here we have negative 12 volts and then negative 8 volts and then plus 4 ohms times I2. I'm not going to write ohms because that takes up space and I don't want to. So that's one we could do, right? And then last but not least, we need another equation for I3. And there's a couple things we could do. We could either do like the same thing going in a circle like that, right? Sorry, we could either do like this loop, or I think equivalently, you could do this loop or like this loop. I think all of those might work. Or this one you wouldn't want to do because you don't know the current going through there. But yeah, let's just do this loop because it's the most straightforward. It's going to be very similar. And now we have 3 equations and 3 unknowns. So this question's kind of chill because you could directly solve these two equations to find I2 and I3, but I'll go over how you would put this into a matrix. So the first thing you want to do is get all of your unknowns on one side and all of your constants on the other. So here we would transfer this and we'd make this, okay, I1 plus I2 plus I3 equals 2. And then we could have 0 I1 plus 4 I2 plus I3 plus 0 I3 equals 20. And then we have 0 I1 plus 4 plus 0 I2 plus 8 I3 equals 20. Right? We see how we got that. And then if you want to solve this with matrices, the way that you think about this is, for those of you who have done matrix multiplication, you could represent this as a matrix equation like this. Right? So that's how you represent it in matrix form. And then there's two ways you can solve this. You can either think of it as saying that your I vector is equal to the inverse of this matrix times that thing you had there, which is, I think, what he said in class. However, in practice, if you have like a TI-84, the way that you solve this is you make a matrix that is going to have your coefficients here and then those there. So you'll have like a 3x4 matrix. And then if you go to the calculator, if you go to the math section and do like your there's if you go to the matrix section of your calculator, there is a RREF method, which you will learn in a linear algebra class, or you can look it up. It gets you the reduced row echelon form, which is what that stands for. But what that ends up doing is it will make it into a matrix that looks like this, where what this is basically saying is this is your I1. So it's still a similar thing where it's like this is your coefficient for I1, this is your coefficient for I2, this is your coefficient for I3. And then in the last column, you're going to have what will actually get spat out as your answers. So I made this take up too much space where it doesn't make much sense. But this you can think of as saying, okay, 1 I1 plus 0 I2 plus 0 I3 equals negative 5.5. Same thing with I2 equals 5. Holy shit, that's bad handwriting. And I3 equals 2.5, right? So that's what this matrix is saying. This is just like a function that you do it on this matrix and then it does that for you. And that's kind of the easiest way to do it. So what I was saying earlier, where the matrix thing is just, it's arguably the easiest way to solve a system of equations, is assuming you get 3 equations or the same number of equations as you have variables, and then you can write them in this form, right? Then you can just take this directly, put it into a matrix, call this function on it, and then you get your answer. Like, you don't have to think at all. You just have to make sure you get the equations in the right form, and then it works. So
Okay, I think why the reason I had a unknown variable though is because in the first problem it gives you it just says I naught instead of a number. But I'm assuming I naught is
Oh.
given though.
No, so in that case, I naught is another variable. So you'd need a fourth equation.
It was saying like find the currents in I1, 2, and 3, not I naught. It never mentioned I naught.
that I was helping someone with that at office hours. Like, I naught is still a variable. They just don't care what it is for the answer to the question, I guess.
So is I naught given to you though? Like you can
No.
assume it's just any number. You have to find I naught.
Yeah.
Oh, okay.
Yeah. So for that for that specific question, you need there's 4 unknowns, so you need at least 4 equations, right?
Okay, I got you.
Because what ends up happening, for example, is yeah, if you don't have enough information, you'll end up with like you'll have some like number for if you do this and it spits out something where it's like some number x y there. What
Yeah, and
this
I had
is
all the
saying,
zeros in the bottom. Yeah, that's what I was
yeah,
confused about.
yeah. What that's saying is you still think of it like this, but basically it's saying that I3 is still undetermined. So think of this in the same way. Here you'd have xi3 plus yi3, right? So
Hmm.
it's saying that there wasn't enough information in your
I
equations to
got
solve.
you. Yeah, that's literally the problem I ran into. Perfect. Okay.
Mhm. Yeah, likewise, if you're ever in a situation where you have 3 equations and 3 unknowns, and then you get something like this, then what that is saying is that actually some of these equations could be used to make the other equation, and you don't actually have 3 unique equations, you have some equations that are just different forms of the same equation. So if that happens, you have to go back and find a different equation that works better. Okay. Hopefully that helps with the matrix stuff. Like again, it's the part of what you should be learning in this class is how to do this. This is the part that matters. This part is like the math stuff that it's just a method to do it. You can kind of do it however you want. However, this is the fastest way to do it. And assuming you do it correctly, it's also the easiest. Okay, now let me find some more questions. All of my practice problems are from previous semesters, and I need to find ones that are good for this class. Okay, yeah, this looks fine. Yeah. But yeah, thanks for the questions. It gives me good insight on what I need to explain. Okay. Okay, and then this is the x. Yeah, so this is saying find Vx and what is the power associated with the 10 amp source. So to do this, we have to do a couple things, right? So let's first think, what do we need to do to find Vx? Well, Vx, that's just the voltage across that resistor. So it's going to be, let's label this Ix just for simplicity. This is going to be Ix times 3, right? Hopefully that's pretty clear. And then next up, we need to find we need to find the power of that 10 amp source. We know that power equals current times voltage. We already have the voltage, so we need to find whatever the current is in this system through that source. So again, I will label that current. So a thing here is when you don't actually know what the current is yet, you can pick either direction for your guessed arrow. So I can either pick saying like this is, I'll call it IY because I did IX there, but like I1, I2, whatever. So I can either pick that direction. I could also pick this direction though. And both things will get you a correct answer. It's just for one of them, you'll get a negative number. And if you get a negative number, it's just telling you guessed the wrong direction at the beginning. So in this case though, I'm going to guess that IY is going that way. So in that case, we know that the power through that 10 amp source, based on my IY direction, we have a voltage drop in the direction of current, and a voltage drop in the direction of current would be a positive voltage, right? So here it'll be IY times 10, and that's a positive 10. It might end up being, again, that this IY is negative, in which case I'll get a negative power, which means that it is generating power, but you can set up the equations like this and your equations will still be right. So anyway, we need to find these things. So how can I go about this? Well, it seems like I need to find some currents. So let's find some currents. And my Apple Pencil battery is low. Hopefully it lasts 15 minutes. To deal with currents, it's usually easiest to do a current equation, right? So KCL at this point? Well, let's do that. So at that point, we have going in 10 amps, right? So remember, if we have 10 amps here, then we have 10 amps here, we have 10 amps here, and that's going in. And then likewise, this is going to be our IY, right? So we have minus 10 amps plus IY plus IX equals 0, right? Because IY and IX are both going out. However, right, we still only have one equation and two unknowns, so we need to find some other equation to write. So there's only like one. If this is what I was saying with your equations have to be unique. If we tried to do a node equation here, what we'd find is that we would get positive 10 amps minus IX minus IY equals 0, right? And that's not actually a new equation. That's just the same equation multiplied by -1. So you have to actually like make an equation that gets you something new. So in that case, we could do a loop equation, right? So what loops can we pick from, right? There's this loop, and this loop. Now remember what the professor said about current sources being tricky to do with loops, right? So we probably don't want to do this loop or this loop because then we have to deal with the current source. We have to think about that. We don't want to do that. Instead, let's do this loop. So I'll start here. So here you do have to be a bit tricky about your positive and negative here, right? So we don't actually know the current through this section of the circuit, right? Because it's between our 10 amps here that we know, and then we've defined IY here, but we don't know what that current is. However, we've defined it as IX going in this direction, right? In that case, our the imagined IX going through a resistor would make the voltage drop go in that direction, right? So if we're working off that assumption, if we're going to then want to use IX in our KVL equation, it's going to be IX times, or 3 ohms times IX. However, the sign for this, if we have our IX, now we have a voltage rise in the direction of the current that we've chosen for our loop. So remember, when you're going around the loop, you pick a direction, and that direction is defining the like imagined like total thing you're doing. It's hard to say, but hopefully I'm being somewhat clear. But here, since we have a voltage rise in the direction of our loop, this would actually be a -3 IX. Next up, for that next resistor, this one is going to be just +3 IY because IY agrees with the direction of the loop that we've chosen, right? So this is our loop that we're looking at, and IY is in the same direction as that loop. So that one gets to be positive. Next up with the voltage source, since there is a voltage drop in the direction of the loop, this is going to be positive, actually. Even though it's a voltage source, that's how it turns out. And then last but not least, we have 4 IY from that resistor on the bottom. And there we go. Now, we have a second equation, and we can rewrite both of these in the standard form. So we're going to have IY, or I'll do X first because that comes first in the alphabet. IX plus IY equals 10. And then if we combine like terms, we get -3IX plus 7IY equals -10. Yeah. And then I can put this into my calculator. So you can, like, there's nothing stopping you from just solving this normally. I'm sure all of you can solve this normally with algebra. But, like, if you want to put this into your calculator, you can do this. And give me a second to do that on my calculator. Let's see. Edit. We're going to have a 2x3 matrix. And it's going to be 1, 1, 10, -3, 7, 10. Oh no, the last one's -10, sorry. And then we're going to go to the math section on the calculator and do RF of the matrix that I just defined. And what I end up seeing is this turns the matrix into 1, 0, 0, 1, 8, 2. So this is saying that Ix equals 8 and Iy equals 2. Okay, now let's remember, why were we finding these in the first place? Because the question asked us to find these two things, and those two things are defined in terms of our currents, right? So now we have to go back and plug these in originally. So we had Vx equals Ix times 3. So it's going to be 8 times 3, and that is 24 volts. Always make sure you remember your units. If you don't, you will get points counted off. And then likewise, we have the power of the 10 amp source is going to be 2 times, ooh, I messed something up. Wait, what did I do? Oh, wait, it was the 10 amp source, not the, ooh, I did, sorry. This whole time I was looking at this. I can go over the power of this as well, but it was asking for the power of this. So doesn't change much. Yeah, so actually, let me just do all three, because I was already doing the other two. So let me just undo. Wait, no, where are we? Pressing the undo button. Okay. 10-volt source, and then let's also find the 10 amp source, but I'll go over that in a sec. So for the 10-volt source, right, it's going to be the power is 2 times our 10, which gets us 20 watts. Unit for power is watts. And since we found that Iy to be positive, that means that the current is actually flowing in this direction. So it's like the battery is fighting against the current. But that's a thing that can happen. That's fine. Okay, then last but not least, let's think about, okay, what would be the power for the 10 amp source? So in this case, remember, P equals IV, and it's still the exact same case, right? We have our current source, and we have a voltage across it, right? So we have some kind of positive, negative. We actually don't know what direction it is, but we can like pick, essentially. And if we get it wrong, then we'll get a negative number, and that tells us what we got, right? However, we've already very conveniently defined Vx, right? So Vx is here. And if you look at the circuit, your resistor here and your current source are in parallel, which means that, it's connected on the top and it's connected on the bottom. As you hopefully know, the voltage of a wire does not change. So that means if I have Vx here, then I also have Vx here, right? So what that means is, first, let's make sure we're thinking about if this Vx is going to be positive or negative in terms of the power here, right? So we know that the current is 10 amps flowing up, right? Because that's what the current source tells us. It tells us that there's current there. Our Vx that we just found down here, so conveniently, is defined like this. And here, since the current is flowing in this direction and we have a voltage rise, then this is going to end up being a negative voltage and getting us a negative power. So the conclusion then is that the 10 amp power will end up being, remember, it's I times V, and that is going to be, oh, I wrote the same thing again, sorry. And that's going to be 10 amps times negative Vx. And we found Vx, it's 24. So then the power of our, that was the 10-volt source. For the 10 amp source, it's going to be 10 times negative 24, which will get us negative 240 watts, right? So that's how you do that kind of problem. So again, it's the steps generally are, okay, what do we need to find? How can I write that in terms of some variables? Then you write equations to solve for those variables. You solve for the variables, and then you plug it back in. And you're just kind of doing that. I did start a bit late, so I'll do like one more problem. I'll try to go a bit faster through it. But does anyone have any like questions or things they want me to go over specifically? If not, then I will just keep going.
Not specifically to any of the problems, but will these be posted at all?
Yeah, I'm gonna upload this to YouTube.
Okay, cool. Thank you.
Mhm. Uh, A lot of these questions are like the same question. Oh, okay, this one's good. So this one's dealing with some like resistors and combining resistors. And this will also touch on something that people mess up sometimes. So this is saying find the voltage of the 60 ohm resistor. So we're trying to find this. So to do that, we just have to kind of simplify the circuit a bit until it's a bit more clear what's going on, and then the answer will probably reveal itself to us. I will explain what I mean by that in a bit, but it should be chill. Oh wait, this is using source transformations. Oh no, you guys haven't learned source transformations, right? That's like there's a thing where you can take a current source in parallel with a resistor and turn that into a voltage source in series with the resistor. I don't think you've done that yet. So in that case, I will actually not do this problem. This is...
I think we just did it today, actually.
Oh, okay. In that case, I'll do this question. But yeah, the thing with this is it's like similar with V equals IR. If I have like, you can do it in either direction, but if I have like a current and if I have a current and a resistance, then, you know, V equals IR, we're going to end up with a voltage of IR and then the same resistor, right? Pretty cool. And that's the thing you can do. Make sure that the connections, it's like this connection and this connection becomes this connection and this connection. Make sure those don't change, but then you can do whatever you want. So with this question here, if we want to simplify the circuit, it's going to be a lot easier if we work with a voltage source here, because then that will make stuff be in series. And you'll see why in a sec. So generally with questions like this, you want to draw the circuit again and again, because it will both make sure you don't mess up and it'll also make it so that your grader actually knows what you were doing, which is more important than you'd think. But here we do a source transform. And now it's looking a bit simpler. We can kind of figure this out a bit better. So first off, we can see these are definitely in series. So I'll turn this into something like this. Yeah. And then let's see. There's like what you'll find in this class is there's a lot of ways to do things. And not sure okay, I'll do this with like just more source transforms because that's kind of the most straightforward way to do it. So one thing that I want to emphasize is when a question asks you something about a resistor, you want to make sure that that resistor does not get turned into anything else in the course of the problem. So like if I took this resistor in parallel with this resistor, you don't know like which one has how much current, right? It becomes simplified into one resistor. It actually would work for this question because it's asking about voltage, and when you put things in parallel together, like the voltage across them still stays the same. But just for the sake of argument, I'm gonna try to leave this 60 ohm resistor alone as much as possible. So almost there now, right? So here I have a circuit that looks like this, and we can actually turn this now back into a current source with the inverse of that transformation, right? So 60, 15, and then this was 7, right? And now it's going to be the current here is going to be 7 over 10. It's the opposite of this, right? Equals V over R. I think, no, 10 over 7. Sorry, that was a silly mistake. And then now I can combine these two, right? And still leave that 60 ohm alone. And remember the equation for this, you can either do 1 over 15 plus 1 over 7, or 15 times 7 over 15 plus 7. That latter one is probably easier. Either way, you end up getting 4.77 ohms. So we have 60 and then 4.77. And then there's like a couple more things. There's 2 more steps. I'm also going to maybe introduce something you haven't explicitly learned in the class, but is very useful. So now if we turn this back one more time, so we do 10 over 7 times 4.77, you end up, the numbers aren't nice, but you get 6.82. You have your 4.77 ohms, and you have your 60 ohms. And if you ever have a circuit like this, where you only have a voltage source and resistors in a loop, remember with KVL, you know that the voltage is going to go up. Like let's pretend this was 0 volts, right? We had 0 volts here. It's going to go up to 6.82 here, and then over the course of these 2 resistors, it's going to have to go back down to 6.82 volts. What you end up finding is that the resistors like kind of get voltage proportional to their size. So here in this case, it's asking for the voltage across this. So we can say that the voltage across that 60 ohm resistor is going to be the proportion of the total resistance. So like 60 over 60 plus 4.77, it's like the total resistance is on the bottom, this resistor is on the top, and then times your kind of like input voltage. And that will get you 6.32 volts. And that would be your answer for that. That's something that I think will hopefully be explicitly covered in the class, but if not, it's like it's a good trick and it's very useful always. So I'll definitely do it in like future weeks again. So don't worry about that. But yeah, I'm out of time. So any very last minute questions? Otherwise, I will end it.
What's your YouTube channel called?
I'll post the link. Don't worry. It's also just my name, Kevin Harris. If you look up Kevin Harris ENGR 210, it'll show up.
Okay, thanks.
Okay, I'm going to end the recording.